Hello everyone. So in the past we looked at some basics of Pytorch, which includes tensors, and within tensors we looked at various operations that can be performed, various attributes that tensors have, and how to move tensors between devices. We also looked at in detail about automatic differentiation and how computational graph is used to compute derivatives and the need for computing derivatives. We also looked at various cost functions in PyTorch. We also looked at optimizers. Today we have an exciting section which includes a PyTorch model template. We will go through what are the elements of this template and also look at a few examples, and in particular we are going to look at linear regression, logistic regression, and a two-layer network. I think after the end of this particular section you should be able to extend this functionality to other kinds of networks. So let's start with the PyTorch model template. So as you see on the screen, the PyTorch model flow has 8 elements. In particular, we are going to do the imports, which is basic for any programming language. We will prepare for data. We are going to create a data loader. Essentially, this will help batch process data sets, examples, and we will look at how to define a model, and this is the most important element of this workflow. We'll also look at how to initialize the model, how to define loss and optimizer. We're going to look at how to train, and then how to evaluate. Now finally we'll also look at two other elements, which is how to save the model and plot any metrics. For example, if you want to look at what is mean square error or the cost function value across iterations. So let's look at the code for imports. So the basic neural network model is within torch.nn, and then you most often this is the structure. This is the short name that is used for this particular module as NN, and this particular module has optimizers, and there are a few utility functions like data loader and dataset. And if you are using vision datasets, then you can use Torch Vision. Here I'm downloading MNIST dataset, so I'm importing datasets and transform. So this is one example of imports elements of this model workflow. Next, we will prepare the data. In this case, we are going to download the data, and most of the functionality will include transforming the data to tensors, and it is encapsulated with this one particular line. But when we are looking at examples, we will see how to convert let's say our NumPy data to tensors, how to do scaling and so on manually when we are looking at linear regression example. So create a data loader. So in this case it is taking these data sets and create a data loader. So this data loader helps us work through the data sets in batches. So in this case I'm specifying the batch size to be 32, and all of the examples in the training data sets I'm saying shuffling is equal to true. So the most important part of this model workflow is defining the model. So you have a model which inherits from NN module. So this any tool network layer or logistic regression or deep neural network, the way you implement is you inherit NN.module and you create your own class, and then you're going to have two functions. One is the initializer, and then the second one is the forward function. So in the initialize functions you are going to always have this particular line of code, and then you can have other attributes here in the initialize, and you define layers here. For example, if you have a linear regression, all you want is one neuron with a linear activation function, so you can define that here. and then we will look at some examples to understand what goes in these components. But for now, this is the structure of defining a new neural network model. And then once a model is defined, you are going to initialize by calling model is equal to my model, and then this criteria is about cost function. So for regression task, you can have MSE loss. We looked at in the past video, or in the past sections, we looked at various possible cost functions, and in this for classification, we are going to start a cost function, define a cost function, and usually we call it as a criteria because we are evaluating our model against this criteria. Optimizer, in the basic optimizer, we are going to use a stochastic gradient with a learning rate as 0.01. And in the training loop, so this is it's going through the number of epochs, and you can see we are getting the train data loader and inputs and labels. So it is going to get 32 values at each of the iteration. So for each epoch and for each of the batches within this train data loader, you're going to get those inputs, and you're going to pass it through the model. This is initializing, so you have initialized your model here, you're passing through the model, and then you're computing the loss. So it will generate some outputs, so you're computing that loss, and then here I'm storing the loss in these particular elements. Actually, you can store loss outside of it as well, but here I'm storing within this. So then optimizers, I am usually you are initializing them to 0 because at every iteration, because it will retain the previous values, and we don't want to do that, so we are initializing the gradient values to 0, and then we are saying loss backward, so that we are computing the gradients and propagating error back to initial layers, and optimizer dot step. So this is the a template for training our model. So once the model is trained, we are going to evaluate model by calling model.eval, and in this course we don't need to track gradient, so we will say with torch.no gradient we are going to do a forward pass and compute outputs. So these outputs, because it's a classification task, in this case you are getting the predicted values, and they're computing the number of positive labels and the number of negative labels, and then you are computing the accuracy by dividing accuracy by total. So for regression task it will be different. For this is an example of testing and evaluation. Again, you can save this model after the training loop itself. So the way to save model is torch.save and model.stakeDict, and you can have your model name, and then if you want to load this particular model, you call model is equal to my model, and then you are going to load all of the weight by calling this particular function, and then you can do model evaluation where you can do predictions and other things. So just recap very quickly. So what we did here, we did some imports, we prepared the data, we are creating batches for our examples, and then we are defining the model. This is, I think, if you understand this particular part, rest of the things are more or less straightforward. We are designing loss and optimizers in the training loop. We are iterating through batch and computing our losses, and we are progressing, updating our weights. We are in the evaluation, we are predicting and generating metrics such as accuracy and so on. Finally, we looked at save models and plot metrics. So now we will look at this particular template with a live example. So here is where I'm importing. So I'm using a real data set to demonstrate linear regression with Pytorch. So you can see these we are always importing torch.nn and optimizers, and there are other things. These are mostly sklearns to load Boston data, to also split our data sets into train, which is standard for other ML programs, nothing specific when we are using this Pytorch neural network module. So all of these are related to plotting, splitting the data, standardized scalar, and computing accuracies. So here I'm importing datasets like tensor dataset and data loader. So data, we are loading Boston dataset, and then we are splitting them into these are the labels, and this is the X values. So X scalar, standard scalar, and we are fitting them, and then we are transforming this into with values so that the mean is 0 and standard deviation 1. Here we are splitting the data set, 80% of the data for training and 20% of the data for test. So far nothing is different from any ML program. So this is where we are converting each of our data sets. These are NumPy arrays, and we are converting them into PyTorch using torch.tensor. So we converted all of these. Also we are changing the view -1 to 1. This is a one-dimensional array. We are changing it to two-dimensional array, tensor. So if you want to understand what the values are here, let's print them here. So here I'm printing y.train, the shape of this one. There are 401 examples and one value. So you can see it's a two-dimensional array. That's dot view -1 comma 1 did, and then the X train is 404 example with 13 attributes, and here are a tensor of y values for 10 values and a tensor of x values for 2 examples. So far we covered this part, and then this is where we are loading the dataset into data loader. So we are taking this X train and Y train and creating a training dataset by calling tensor dataset, and the tensor we are also creating data loader by adding train data, and we are specifying the batch size. So far I think it's straightforward. Now this is the crucial part where we are in the previous template we called my model, and we passed NN.module. Here, because it's a linear regression model, I'm naming it as linear regression model. You could simply name as my model as well, or you can name it as a linear model, whatever makes sense. So within that, you always have a, because we are inheriting, this is so this is a constructor where we are calling the constructor of a neural network module by saying super, and we are passing in our linear regression class, and then and the self, and then here this is where we are defining our layer. What we are saying here is self.linear is nn.linear. So nn.linear is a type of a neuron with a linear activation function which takes in n features, and we are saying the number of outputs from this one is going to be 1. So what happens within this particular code? So there will be x1, x2, and so on to x30, and then we are getting an output, and this is only one value, and this is, so here this is one value, and then n number of n features is these, and here the activation function is a linear activation function, which means we are doing wi xi, and then we are summing, and then we are getting this by hand, right? So this is the output and this is the input. That is what we are defining within this particular line. And the forward function, in the forward function, we are passing through our this model, this layer, and it will do this operation and it will get the output by hand. So that's what we are defining here. And model initialization, so we can initialize the model by calling linear regression, and we can pass the shape. You can see that in this we have defined our constructor to be n number of features as input. So we are passing shapes.1, so that will be 13, so that will be passed here. And then we are defining loss and optimizer. Because this is a regression problem, we are using MSE loss, and also we are creating a basic optimizer, stochastic gradient descent with model parameters and LR 0.001 learning rate. Loss values I'm storing it every iteration, so number of epochs I'm defining it as 100. Remember, epochs is the number of times all of the examples will pass through the network. So in this case there are 400 something examples, and 100 times they will pass through the network, irrespective of the batches and so on, right? So we are going through 100 epochs, and in each epoch we are going extracting a batch of 32 values, and then we are making we are clearing gradients, and then we are passing 32 examples to this network, and then we are computing loss for the inputs that we are given, and then based on the outputs and the known target values, and then we are back propagating the error and updating our weights here by calling optimizer.step. Then these loss values are stored after each epoch. Remember, not exactly after each batch, but after each epoch. So this is the training part, and then this here we are saving our model as model.stateDict, and we are giving the name as a linear regression model CKPT. So if you want to load later, we can create my model is equal to linear regression model, and then we can load this particular the saved model. And then when we are doing predictions, we have to say torch.noGradient, and then we just pass x test through our model. This will have predictions which are linear in nature. And to compute MSE, you have mean square error, y test. I'm getting a NumPy values, and then and I'm also getting predictions. So you can print the MSE. You can also do the plotting values, model loss across iterations. So you can see it did not improve after 20 iterations. So I think this will conclude linear regression. So similarly, we will okay. So the most important part is how to define this linear regression model. I have few more details listed here. You can pause and go through what that means, but I'll go through. So let's look at a logistic regression with a multi-class example, end-to-end example. So the first step is to import all required modules, which are similar to linear regression that we did before. These are all sklearn related modules, mostly to load iris dataset and then train, test and split, and also apply standard scalar and compute accuracy score. So here we are loading iris dataset. So iris dataset has three classes that we need to identify different species of iris dataset based on four attributes: sepal length, sepal width, petal length, and petal width. So here we are doing scalar operation. Here we are splitting train and test dataset. So this is standard for any ML algorithms that are there in sklearn. So this is where we are converting them into Pytorch tensors. So from numpy array we are defining the data type and then saying torch.tensor. So this is straightforward. Once you have extended x, y, we create a train data set by calling tensor dataset, and the tensor dataset can be fed into data loader, which will convert this dataset into batch size of 32 samples. So when you're running through training loop, it will send 32 samples at a time. So here is where we are defining logistic regression model. So here we are NN module is we always inherit this particular module, and we have I'm passing two arguments in the constructor, n features and n classes, and then this is always whatever model you are specifying, you call the constructor of superclass, which is NN module, and then you are defining what you are doing with nn.linear is the layer that I'm defining here with nn.classes, and then in the forward step I'm passing through it. So you may be wondering, how is this logistic regression? I'll explain that in a later, but let me explain what is the architecture for this particular code is. So here we have 4 inputs, and then we have 3 classes, right? 3. So each of these inputs will go. So you have W1 1, W1 2, W1 3, and same thing here. You have W2 1, W2 2, W2 3, and so on. So you get a value for each of these. So this is the architecture that we have, and we have a weight W1 for this particular input layer. You have W1, W2, and if you consider from the output layers point of view, so O1 will be sum of W1 x1 plus W2 W11 x1 W21 x1 x1 and so on, and you get a corresponding value. So ideally you would want to, in a linear regression model, we either in a logistic regression model we often apply softmax function, or if it's a binary classification we go through a sigmoid function, but you don't see that in this code. And the reason is because we are using cross entropy loss, and cross entropy loss will take the outputs, the linear outputs, and apply a softmax, and also on the log values, and then apply negative log loss function. So because this is already taking care of the softmax part, we are not explicitly specifying in the output layer. Here we are not specifying either sigmoid function or softmax function here. So I'll show you the code to understand what I mean. So for example, in a binary logistic, this is how you would want to code. For example, here you want to code self.linear, and then in the forward path you want to pass those values through a sigmoid function if it's a binary logistic function, but because the loss function is cross entropy, it already has softmax built into it. So it is a practice to apply in the loss function rather than outputting a softmax and then doing a negative only negative log of those outputs. So that's the reason why I did not apply softmax. So rest of the code is very similar to linear regression, number of epochs and data loader, and we are passing we are zeroing the gradients and then doing a forward pass on the inputs. We are computing the loss, and then we are storing the loss after each epoch, and then finally we are saving the model as logistic regression, and then we are doing the prediction and the test set by essentially calling model.x test. And here we are calling a dash predicted is equal torch.max and prediction data count 1. What it does is it results the highest value and the predicted class. So because we are not interested in the value but only the class, so the index, this predicted class will be the index where it found the highest value. So so it will be either 0, 1 or 2, and then from there we can compute the accuracy by test and predicted value. We can compute the accuracy, and this is how the accuracy the loss is shown here. If you want to understand the data set, it has 120 data points, and then the training has 120 data points. 4 values are the attributes, sepal and sepal width and so on, and then the tensor output, the y values are 0, 1 and 2, indicating which species of iris it is, and then the tensor values for after scaling is shown here. So an explanation of why what a cross entropy loss function does is provided here. So I'll not go into detail, I already explained this one. Finally that will apply the same template on 2-layer neural network to solve an MNIST problem. Right? So again here we are also we are importing the torch modules, torch vision, matplotlib, and here I did not use sklearn modules because I'm getting the data from torch vision itself. So from the torch vision I'm downloading MNIST dataset into train dataset, and also then into test dataset, and then converting into batches of size 64. Then so the input size is 74, hidden size is 500, and number of classes, output classes is 10, and number of epochs I'm running is 5, and the learning rate is 0.05. So here is where we are defining the neural network architecture. So this is fully connected layer where the input size is 784, and then the number of layers, next set of layers is 500, and then we are defining what the activation function should be on all of these hidden layers, we are defining it as a ReLU, and those 500 layers will go into next fully connected layer, and we are defining it as a linear where the number of classes, input size is the hidden size, and the number of classes is 10 for MNIST dataset. So this is really straightforward. Again, we are not applying any activation function after this, because we are our criteria is cross entropy loss, so that already applies softmax function, so we don't have to apply ourselves the activation function here. And in the forward pass, we are essentially going through the network where we are passing our input values into first fully connected layer, and the outputs of that will be passed through activation function ReLU, and then whatever the output comes, we are passing through the second fully connected layer, and that is the output we are generating from forward. And so again, the loss function is defined as cross entropy loss. The optimizer here we are using Adam with a learning rate of 0.001, which is specified here, and we are training the model here for number of epochs. I'm storing the loss function. So So what I'm doing here is I'm going through each of the trained dataset and I'm reshaping that into a single dimensional array. And then I'm passing through the model, and then I'm passing through the loss function. Of course, I have to zero grad as ingredient to 0, as I've done in the previous functions as well, and then calling computing the gradients and then updating weights. So at each step I'm printing the values, and then I'm also saving the, once the training is done, I'm saving the model as let's say 2-layer model .ckpt, and here I'm computing the accuracy by total number of I'm computing number of correctly predicted values, and then the total values, and then computing the accuracy as total number of correct by total. So finally I'm plotting model loss and iteration. So I did not have Torch Vision already installed, so I could not execute this yet, but this code actually does work in which I tested in a different notebook. With this we wrap up this section of the video. So what we did, we looked at Pytorch model template, where we defined there are 8 steps to do, and the most important step of them is defining the model, neural network model. Then we looked at logistic regression, linear regression with a Boston dataset, and then we looked at logistic regression multi-class with iris dataset, and then we looked at a 2-layer neural network with 784 as the first layer, and the second layer has 500 fully connected layer, and the output class has 10 layers, and we defined a neural network in this manner, and the rest of the code is very much similar to what we have done for the linear regression and the logistic regression. We also discussed why we are not providing the activation function in the last layer like softmax, because cross entropy loss already does softmax operation, so we don't have to specify explicitly. So with that we wrap this particular section. I want to show you the output of this particular 2-layer neural network. When I showed in the past, it would not run, but I was able to run it in this notebook. So you can see it started downloading the data sets initially when we are calling train data set and we are saying download is equal to true. So it downloaded the data sets, and it is running epochs, and in each of them we are providing certain number of data sets. So it's providing it's printing out the loss value at every 100 steps. So you can see the final accuracy of the prediction is 97.809. I think we can still improve upon it, and then the plot of the loss is shown here.